Okay, section 13.5, which is curl and divergence. Okay, and like a lot of things that we've done in 3D, sometimes these are hard to visualize, hard to figure out kind of what's going on here. But it helps if we think about the vector fields that we've been looking at. The only problem is that these are going to be often in 3D, but we can make the correlation to 2D vector fields. Basically, some basic ideas here. Curl is actually going to be a vector. Divergence is a scalar. Okay, and curl will give us the tendency for rotation in the vector field. Okay, and I'm actually going to share with you some vector fields to kind of look at here. But tendency for rotation in a vector field. And divergence kind of tells you, if you think of your vector field as like fluid, it measures the change in density. And I guess it doesn't even have to be fluid, but change in density, density in a vector field. Okay. So I can give you some examples here. If we have a vector field that, and actually I'm going to draw or use a computer to graph this one for you later, but if I have a vector field that looks like this, so I'm trying to make all these arrows the same length, smaller on the inside, bigger as we move out. Okay. A vector field that looks like this obviously has curl because you can see rotation in it. Okay, so curl is not 0 here, okay, or the 0 vector. But also here, the divergence is 0. Okay, because if we're along any sort of path here, the arrows don't get any closer together or farther apart as we stay on that path. Okay, so you think about if we're to stay on that path. Okay, so the arrows aren't getting any closer together or farther apart. We could do another one where, let's see here. If we have something like this. So these are all the exact same arrow. Okay, in this case, the curl would be 0 and the divergence is 0. Okay, so the curl would be your 0 vector. There's no rotation here. And your divergence would also be 0. Okay, because those aren't getting any closer together or farther apart. Okay, I'll give you one more example because you probably want one where the divergence is not 0. I'll actually give you 2 of them. Okay, on this one, I'm going to do little arrows pointing out. Oops, they should all be pointing out. And then moving on to bigger arrows pointing out. Okay, and then, oops, I already have the other one drawn. Okay, this one would be the opposite, pointing in. Okay, in the green one here, let's see here, the curl, I believe, I'd have to think about it a little bit. The curl is 0. We have no tendency to rotate there. Okay, I'll try to graph that one in a little bit. But what's more important here is that the divergence is less than, or I'm sorry, it's actually greater than 0. Okay, we are diverging here. Okay, if any point that we look at, okay, that vector field is pushing out from there. Okay, oops, I didn't mean to change the angle on them there. Okay, we kind of have what would be called like a source at the origin that pushes everything away. And so we are getting less dense, okay, as you move away and you're moving with the flow. As you move with the flow, you get to less dense areas, okay? This one to the right here, the curl would also be 0, I believe. But the divergence is less than 0. We're kind of, it's almost like what we would call a sink. We're getting compacted towards the origin, and we're getting denser and denser if you go with the flow. Okay. And again, you can kind of think of all these as like fluid. Okay. Whereas that blue one in the upper left is almost like a whirlpool, right? It's curling around. Okay. The one in the purple is just a stream flowing. Okay. And in the green, you can almost think about it as like a sink backing up. Okay. Like we're pushing out here. Okay. And then the one in the red, they're almost like a drain. Okay. So, and I'm sure, if this explanation isn't clicking with you, definitely like look on Khan Academy. I know he has some good videos on curl and divergence. Any other resources that you might make it click better, and maybe even share that with me too, because this is always kind of a tough one for kids to get, and sometimes some resource will help them understand it better. So let me know if you find anything good out there that does a good job explaining curl and divergence. Okay, but we're just going to get to some pretty basic formulas here, and then I'm also going to show you vector fields, and we're going to calculate some curls and divergence with a calculator, just so you can get more of these ideas here. Okay, so let's go with curl first. Okay, so it all goes back to, again, your vector pi plus qj plus rk. Okay, and then the curl of f, this is going to seem confusing, but there's an easy way to remember it. It's the partial of r with respect to y minus the partial of q with respect to z, I, because remember I said curl is going to be a vector, dp dz minus dr dx, j. Okay, and then plus dq dx minus dp dy k. Okay, now, like I said, that's pretty tricky to remember, but we have this special operator that we use called the del operator, which you've seen before. Okay, it's called your vector differential operator. Vector differential operator, or just del for short. Okay, and del is I partial dx plus j partial dy plus k partial dz. Okay, that we can remember, right? Because everything goes in order, I, j, k, x, y, z. And then remember, we've seen this before when we've done gradients. The gradient of f, we would apply that del operator to get your gradient, right? We've seen that, okay? Well, curl is del cross f. Okay, so we do our cross product. So what we do is we have the ijk going across the top. Okay, and then d dx, d dy, d dz. So far not too hard to remember. And then pqr. So everything's in order, and then we do this just like we would a cross product. Okay, so when we do the I part, okay, we're going to write dr dy minus dq dz, right? AB minus CD I plus, now we're doing the J part. So dr dx minus dp dz, but remember, and when you're doing your cross product, that whole second one term is negative. So we just do like the double negative there. Okay, so rather than doing dr dx minus dp dz, we're going to do dp dz minus dr dx. Okay, and then we do our k. And so now we'll have dq dx minus dp dy. Okay, and that's how you remember curl. Okay, and again, this is kind of a measure of rotation. Okay, if you get your curl of f equals 0, then we have no rotation. And if you remember that from the previous lesson, that means that we have a conservative vector field. Okay. All right. So let's do an example here. And again, these are all 3D, and then when I get to the plotter, I'm going to do 2D. So some of these won't transfer well to the plotter, but we'll get there when we get there. Let's see here. Let's do purple. Okay, so an example is if we just have, and I think this is number 4 in your book, the vector sine yz. Oops, I didn't mean to do a parenthesis there. Okay, and we're going to find the curl. So what we're going to do is what we just did above with that cross product. So we're going to cross I, j, k, d dx, d dy, d dz, and p will be the sine of yz, q is the sine of xz, and k is the sine of xy. Okay, so our cross product there, so we'll have d derivative of sine xy with respect to y. Okay, so the derivative of sine would be cosine xy, and then times the constant x. Okay, minus the derivative of sine xz with respect to z, so cosine xz times x. Okay, and that will be in our I direction. I'm just going to do component form there. Okay, and then for j, remember we're going to do it in the opposite. Okay, so we're going to do sine yz with respect to z, so that will be y cosine yz minus, and then we're going to do sine xy with respect to what? X, so y cosine xy. And then for our z component, we'll have the derivative of sine xz with respect to x, so z sine xz minus the derivative of sine yz with respect to z, so y sine yz. Oops, I don't know why I switched to, those should all be cosines. Forgot to, cosine should be there, cosine should be there. Okay, got that fixed there. All right, so that is not a 0. So that would tell me that there is some rotation in the plane. Okay, or actually, sorry, in vector space, 3-dimensional space. So there's some sort of rotation going on there. Okay, and then it's not a conservative vector field. All right, we're going to do, as you might be able to guess, a next one that will end up being conservative. And I think once we get to our 3D plotter, we could probably just graph the x and y components too and kind of, we'll mess around with it. Okay, and I'll show you a nice tool that you can kind of mess around with. Our next one, f x y z, is going to be I plus sine z j plus y cosine z k. All right, so same thing, we're going to find the curl here. So, got my I, j, k. I've got my 1, oops, getting ahead of myself, d dx, d dy, d dz, and my 1 sine z, y cosine z. Okay, so I direction, we're going to have, hold on, the derivative with respect to y, so it's just going to be cosine z, and then minus cosine z, I plus, now in our j direction, there is no x in y cosine z, so when we take our derivative with respect to x, it's just 0, minus, oops, and I mixed those up, it's not going to matter anyways because they're both 0. But then the derivative of 1 with respect to z would also be 0, k, plus, and then your derivative, let's see, now we're going to do k, so d dx of sine z, which will be 0, minus d dy of 1, which is 0, j. So we get the vector, the 0 vector. Okay, so this would be a vector field with no rotation. All right, and we can draw, so we know that it's conservative, so now we can find that, remember that lowercase f, xyz, such that the gradient of f is that big F. Okay, so remember we do that with integration. So f should equal the integral of 1 dx. It should also equal the integral of sine z dy, and the integral of y cosine z dz. Okay, so the integral of 1, that would be x plus possibly some function of y and z. Okay, plus c, right? Or k, I think your book uses. The integral of sine z with respect to y would be y sine z plus some function possibly of x and z plus a constant. Okay, and the integral of y cosine z with respect to z, the integral of cosine would be sine, and that y is a constant, so that's working out nice. Y sine z plus, oops, and you know what? I did f and f twice. I'm going to do g there. Okay, okay, plus h of x and y plus c. Okay, well, we can see here then that this f of yz, that has to be y sine z. Okay, g of xz has to equal x, which is also h of xy. Okay, so we've got everything accounted for. So f, that lowercase, will be x plus y sine z plus some constant. Okay? All right. That's your curl for you. Okay, that's the basic idea there for curl. Now we're going to look at divergence. I don't like that light blue color. Where's all my colors? Ooh, dark blue. Okay. Divergence. So again, divergence has more to do with like the density of the flow. So think about in your vector field, if these arrows are getting closer together or farther apart, okay? And also, we'll take a look at one too where they're not necessarily getting closer together or farther apart, but getting longer versus shorter, okay? Because you're also trying to like squeeze more into a smaller space. You can kind of think divergence is like as we're moving through a point too. Like, are the arrows that go through that point getting closer together or longer? So we'll talk about that. Okay, I don't want to get too far ahead. I get all excited here. So again, you're going to have this vector pi plus qj plus rk. Okay, and your divergence of f is dp dx, dq dy, plus dr dz. Okay, and we've seen this before, right, when we did gradient, okay? But we're adding them together. We're not keeping them separate as a vector. So remember the gradient of f would be dp dx, dq, dy, dr, dz. Okay, so what we're doing here, the divergence is more of a dot product because we're going to add them up. Okay, and you're going to get your scalar then. All right. Oops, and I should make this. Okay. All right. So if we also have a special case here, if the divergence of f is 0, then f is what we call incompressible. Okay, and again, that just means that we're not like compressing it like what we showed at the top here. Sorry, my chair's squeaking. Okay, so it's easy to see how that's like compressible, right? We're compressing everything into the origin. This is like the opposite of compressible, like we're spreading it out, but same idea. Okay, so those would be two where the divergence is not 0, so they're what we'd call compressible. Okay, this one here, divergence is 0. We're not getting any sort of compression here. Okay, everything's just flowing smoothly. Okay. Did I write in or im? It should be incompressible. Okay. A couple properties here before we get too far. The divergence of the curl of f is 0. There is a proof for that in your book. Okay, it's kind of interesting property there. All right. If we do the divergence of the gradient of f, then we get del dotted with del f like that. Okay, it's like a second derivative. And we would write it like this. Okay. And we also have a special name for that. Just like this is del, this is called the I'm probably pronouncing his name wrong. Laplace operator. It's one of those things that I've read and not really heard, or maybe I have heard it and just wasn't paying attention in my lecture. I don't think it's Laplace. You know, maybe it is though. Laplace. Laplace. I'm saying it like a true Midwestern. It's you're a Laplace operator. Okay. All right. Let's do a little bit with this guy. Okay. So if we go back to the exercise we had before, where f x, y, z is sine yz in the I plus sine xz in the j plus sine xy in the k. Okay, then your divergence of f. Okay, remember it's the partial of p with respect to x, which in this case would be 0, plus the partial of q with respect to y, which would also be 0, plus the partial of r with respect to z, which would also be 0. Okay, so this one would be incompressible. Okay. All right. We're going to look at the next one, which I have written down as either example 8 or exercise 8 in your book. But but I'm going to draw this the best I can. Okay, so what we have here is arrow, a little bit longer, a little bit longer, a little bit longer. Okay, and then it's pointing up a little bit, up a little bit, up a little bit, and then up more. And then up a lot. Okay, so what I'm trying to do here is that in each column, the width of those arrows is the same. Okay, so if I just look at the X component, it's the same in each column. And if I look at the Y component there, how tall it is, it's the same in each row. That's what I was kind of trying to go for there. Okay. So I can't even remember what the problem is asking here, but I think they're asking to determine if the divergence and curl are either positive, negative, or zero. Okay. So our divergence of F, hopefully you can kind of tell by looking at it that it's greater than zero. Okay, because again, if we go with the flow, we're spreading out. Okay, one thing you can also tell here is X, so remember your divergence of F is dP dx plus dq dy plus dr dz. And well, there is no r here, so r is 0. Okay, and F here, remember, is p q r. Okay, so the fact that this is 2D tells us that r is 0. Okay, and then dP dx. So if we look at that, how our vector is acting in the x direction, which is p, right? As x changes, there's a positive change there. Okay, so dP dx is greater than 0. As x gets bigger, the actual length of the vectors is getting bigger in the x direction. Okay, and then same with y, dq dy. So if you look at our function that's giving us the y component, as y gets bigger, that's also getting bigger. So dq dy is greater than 0. So dP dx is positive, dq dy is positive, dr dz is 0. So the whole thing then, the divergence of F must be greater than 0. Okay. The curl is a little bit harder to visualize here. But remember your curl of F. First of all, I didn't intend to draw any sort of rotation there. It almost kind of looks like there is rotation, but hopefully you can look at a vector field and see like there's no rotation. I'm actually going to give you an example of one in a little bit that I feel like there is rotation, but I'm getting ahead of myself again. Okay, anyways, your curl is dr dy minus dq dz I plus dp dz minus dr dx j plus dq dx minus dp dy k. All right. Now, first of all, r is 0, so that would be 0, and that would be 0. Okay. Now, the next thing is, now Q tells us your X component again. I'm sorry, Q tells you your Y component. P tells you your X, okay? The fact that R is 0 tells us it doesn't matter where we are in the Z direction. So anything, like if I were to put another layer on this, like say this, what I just drew is when Z is 0. If I drew another layer when Z is 1, I'd have the exact same graph, okay? So Q doesn't change as 0 changes, and as Z changes, and P doesn't either, okay? All right, now all we're left with is dq dx and dp dy. Well, remember, Q describes your y, and P describes your x. Okay, P doesn't change as y changes. Okay, so if we're at, P only changes as X changes, like from 1 to 2 to 3 to 4, whatever. Okay, P doesn't change when Y changes. If I'm at Y equals maybe 1 here, P is the X component. If I move up, P is the X component. Okay, so there's no reliance on P in the Y direction. And then we see the same thing on Q in the X direction. Okay, that Y component is the same when X is constant. Okay, so 0, everything is 0, and we have no rotation, no curl. We've got a conservative vector field there. Okay. All right. One more thing. All right. Is we have Green's theorem with vectors. Okay. So I'm going to switch to my green pen here, right? Okay, the vector form of Green's theorem. Okay, so F, again, your vector, Pi, no arrow over the P, plus Qj. All right, and then we have our line integral over a closed curve of F dot dr. P dx plus Q dy. Okay. Right, because dr is dx plus dy. I guess dx in the I, if we want to do that, dx in the I, dy in the j, because r is xi plus yj. Okay. And then again with your Green's theorem, that's the double integral over the region of dq dx minus dp dy dA. Okay. So if you remember, your curl of F is I, J, K, d dx, d dy, d dz, pxy, qxy, and 0, because we're working in 2 dimensions here. Okay, so when I take my I component here of my cross product, I'll have d dy of 0, which is 0, minus d dz of a function q that's defined for x and y. So that would also be 0. Okay. Same thing's going to happen in my j direction. Okay. d dz of pxy will be 0 minus d dx of 0, which is also 0. Okay. And then in my k direction, I'm going to have the partial of q with respect to x minus the partial of p with respect to y. And that will go in the k direction. Okay, so our integral of f dot dr can be described as the integral over d of the curl of f dot k dA. Okay, again, because the curl of f would be 0, 0, dq dx minus dp dy, right? And then if we dot product that with 0, 0, 1, your unit vector in k, right? Then we get this. Okay, and that k is that we drew here. Remember that k is just a unit vector in the z direction. Okay, so it is just 0, 0, 1. So we can't just plop the curl of f in there because curl is a vector. Okay, but if we dot product with k, then we have a scalar. Okay, and then we can integrate that. All right, we can also show, and we're not going to end these notes right now, that your integral over a closed curve of f dotted with the normal vector of ds is the integral of the divergence of f xy dA. Okay, that's your line integral of the normal component. Okay, and I'm not sure if they do that in your book or not, but that's another thing, another property that we can have here. Okay, so that might come up a little bit too. Okay, so I was just looking here in my notes. Well, I guess I did kind of show it in my notes here, that your normal vector, I'm going to hold off on that. Okay, but these are two important links between curl and divergence and Green's theorem. Okay, now what I wanted to do, what I've been kind of talking about doing, is I'm going to share with you Wolfram Alpha, Wolfram, okay, has some widgets that you can use to help you with these. Oh, it's already showing up there, okay, and not necessarily for like to get answers, but to kind of wrap your brain again around how some of this works, okay. So I'm going to draw in, first of all, oops. If we just do 1, 2, oops, I should be over here. Okay, we're going to do a vector field where the I component is 1 and the Y component is 2. Okay, so we're just going to draw that vector field. Okay, and that's what it looks like. Okay, so a couple things to note here is that I see no curl, right? There's no rotation there. And I also see no divergence. Okay, I don't see those arrows getting longer or shorter or closer together or farther apart. Okay, and I can confirm this, right? This is another widget here where I can put in a vector and it will tell me the divergence or the curl. So I'm going to do curl first, actually. And it's going to compute it for me. And there you go. I can see that the curl is 0. Okay. And then I'm going to do the divergence. Okay, and I also get that the divergence is 0. Notice the curl was a vector and the divergence is a scalar. Okay, let's do another one here. We're going to do a circle. So we're going to do, I think I had it up here before even, negative y for the x and x. Okay, compute this. So there's my vector field, and I can definitely see we've got curl, okay, but no divergence. If I follow a path, I'm not getting any more or less dense there, okay. So let's just kind of check that. All right, so again, we want negative y and x. Okay, there's the divergence first we're going to do. Divergence is 0. Okay, and again, this is one that you could easily hand calculate these two. Okay, and then my curl. Okay, notice my curl vector, it's 0, 0, 2. 2 is in the z direction. Okay, so when we're talking about curl, any sort of rotation, the curl will be pointing away, perpendicular to the rotation, to the field of rotation. Okay, so the curl, when all the rotation is showing up in the xy plane, the curl is in the z direction. All right, go back to that. Okay, we can do it. You can keep trying these too. Let's do. Let's see. I want to do x is 1, and well, let's do y is x. Let me see what that one looks like quick. See if this is the one that I wanted. Let's see here. Not quite. Let me do. Oh, you know what I wanted? I wanted x and x. Okay, so what you see here is that the arrows are pointing, like if we look in the first quadrant there, okay, they're all pointing at the same angle, but they get bigger as you move away. All right, so if we do this one, curl, the curl on that is 1. Okay, there actually is some rotation there, and I was trying to think about the best way to explain it to you. And I didn't come up with a great one. But you would have to think about, like, when we're hitting that 0 velocity, something's going to move it along. And in fact, maybe if I'm going to do another one in a second. Here, let me do the divergence on that one, because that's what's really the more important one. Your divergence there is 1, okay? And that's because we are getting bigger arrows as you move along the path. Okay, that flow is increasing. Whereas remember, when those were all the same length, the divergence was 0. Okay, keep messing around with that. Here's another one that I like, which is kind of similar to the one that I just had. That's why I kind of didn't spend too much time on it. Let's, instead of x and x, do the absolute value of x and the absolute value of x, and I think it's a little bit easier to see. Okay, so if we think about this as being like flow of a river, okay, and think about like a leaf floating on the river, if it gets stuck here in the third quadrant on a fast flowing river, it's going to follow those flow lines, but can you imagine it's not going to just stop when the velocity is 0 and it's done? Like, I can't imagine physically how that would happen. What's more likely to happen is it's going to flow along these, and when it starts to slow down, it's going to curl a little bit. Okay, it's going to find like one of those faster paths again. It's going to still kind of go down the stream almost like this is an asymptote at the y-axis. It's never actually just going to hit the y-axis and stop. Okay, so it's kind of a weird one to think about there. But here, if we do our little widget here, we can see divergence there is definitely not going to be 0. And notice that divergence has to do with absolute value, right? If we are moving away, the divergence is going to be positive, like in the first quadrant. In the third quadrant, the divergence is going to be negative. Okay, so again, where that positive divergence hits the negative divergence, we're going to have some sort of curl going on there. All right, and then the curl, just to confirm, curl is also dependent on the absolute value of x. Okay, but yeah, feel free to graph any, and again, the examples that we all did were 3D, so they're kind of hard to graph, but kind of think about like, what might this look like in 2D, or if there's y's and z's, what if I just make them all y's or something like that? And you can kind of mess around and just get kind of that intuition of, here's a vector field, here's what I think about the curl, and here's what I think about the divergence. All right.